Hi, everyone. Dennis here. Let me just get going. The big kind of plan for today is to, from zero, set up CodeLogician, install it, make sure it works, get it to work with Claude Code, and also go through a bunch of commands that you will find useful. And the things that will follow through, you can actually go and check it out online. It is on GitHub, Imandra AI, CodeLogician demos. So that's there's an intro folder. That's what. Okay. So hopefully you can see this. This is the new Imandra X website. Lots of other changes are coming soon online. The way to start using Imandra X in VS Code, and there are also kind of analogous plugins for Cursor and anti-gravity and other tools that are, I think I forgot the exact address for the open source VS Code extension like repository, but it's all there. So you can, everything that you see us using in VS Code, you can also see, you can also use it out of Cursor and all those other tools as well. So yeah, the new Imandra X website is pretty cool. And if we go to documentation page, we'll get some nice introductory texts, things like the first proof, etc. We will today go through, and we'll be calling these things out of CodeLogician itself, but something that might be particularly interesting to you is this concept of region. This is part of region decomposition. Analysis of the state space. And this is kind of one of the main workhorses that we use to also generate test cases and perform other types of reasoning. This is the new Imandra X website with pretty new documentation page, which I highly recommend you check out if you want to use CodeLogician. Okay, now let's start to go through actual CodeLogician setup. So you can see from our website here, we have kind of two ways to install the CLI utility. One is by just using curl. So this is installer. This is the one that I would actually recommend everyone uses. Basically, it's not only does it install the utility itself, but it also sets up the Python. So it's kind of its own environment. So it doesn't mess up what other things that you have. Or you can just do it via pip. So we'll use this one, and then we'll kind of start and get this going. So let me just, and this assumes that first you obtain the Imandra Universe API key, which you can get at universe.imandra.ai. So this is the kind of our API platform for all of the reasoning tools that we provide. So you can see CodeLogician is one, obviously Imandra X. There's many others there as well. It's free to start. So just create an account for yourself. Once you're there, just create an API key. And the tutorial that we have, we will assume that this is basically Imandra _uni_key, all caps, is in the shell. Okay. And I have two terminal screens here. All right. So if we do CodeLogician, we have nothing. So why don't we try to do something crazy, which should never be done, but I'll do it anyway. We'll do a live installation and live kind of action. So let's try to do this thing. Okay, and we should be done. That's all that it takes for us to do this. So if we now do this, if we do Logician help, we should, it's a bit slow on the first time because I think it's just compiling and kind of redoing everything, but it should be the caching stuff, but it should be faster on all of the kind of the new things here. So perfect. So this basically, that's it. We're pretty much done. So you can see there's a bunch of commands here. We will today go on this kind of doc and eval. So those are really the two commands that you want to focus on when you're working with tools like Claude. So now that we have this, basically, the fact that I ran this help command with CodeLogician, it also means that my Imandra _uni key is set up correctly. So if it wasn't, it'll basically show this to you, etc. So let us, and actually before we even go on, so you'll see other tools that we have for CodeLogician. So for example, VS Code extension, the MCP server. So this agent command here, this in itself is a LangGraph based agent that you can invoke, and basically performs auto formalization into IML for, I think, about a dozen different languages. This was started before things like Claude Code, etc. All of these CLI tools really kind of took off. So it's still there, and we have corporate and enterprise customers that for various reasons cannot use things like Claude Code, etc., but they make heavy use of that. And especially you can also download VS Code extensions. So if you search in VS Code, and again, all the other IDEs as well, if you search for CodeLogician agent, this will be basically this command right there. And multi-agent, so this is if you want to run it on a directory that, let's say you have a directory with a bunch of, let's say, Python files that all kind of link each other. This is something that goes and creates a effectively a meta model out of all of those files, etc. But again, those are, I would say, pre things like Claude Code, and they're still used within enterprise environments and enterprise customers that we have. But my kind of recommended way of using CodeLogician now is via tools like Claude Code. So without further ado, let us start Claude in this. Yes, so I'm going to trust this. Yeah? So what I want to now do is I want to teach Claude about CodeLogician and how to use it. So learn about CodeLogician, executable inlet path by running its help command. Let's see what happens here. Okay, so if we do CodeLogician doc, which is kind of this documentation that we have. So we have this ability to dump an entire skill. So a bunch of files that we can use to teach Claude how to write IML code, how to interact with everything. So if we do, let's just go dump, let's call it skills. Okay, so if we go to skills, we now see all of these things. So, for example, okay, so learn about IML and other ways to use CodeLogician from the skills directory, which contains info from. Okay, so that should get us started. So once you kind of do this, then Claude becomes a grandmaster of everything IML and CodeLogician, and that should really be sufficient for you to use CodeLogician within Claude or basically other. Yeah, you can see here it's actually learning what the different operators are, all of these different things like that. So while that is going, let me go into this. Let's just go to so this intro, and this is the set of um, introductory IML snippets that I want to go through and kind of look at the different functions, especially the eval command that I would say that would be the kind of the main workhorse of using Claude together with CodeLogician, etc. So without further ado, let me go to this guy. So this is in that, again, this is the repository CodeLogician demos. Let me make this bigger just in case. Okay. So, and you can see here, I have the Imandra X plugin or extension installed out of VS Code. And this is the Imandra X.dev will walk you through how to create it. But you can see here, for example, all of this code that we're going to be feeding to CodeLogician, we're already kind of getting it here as well. So this is a very kind of useful companion for running CodeLogician. So, okay, let's go through. Actually, there's open chat. Let me see this. Oh yeah, perfect. Let me go through this stuff. Open preview, so it's easier to see. So, okay, prerequisites, we have done this. We have installed this stuff here. Okay, let us now look at, let's see this, IML errors. And yeah, let's see what an error looks like. That's the first one. So this guy right here, you can see it's all actually syntax and, etc. Let's actually, let's actually first get one test there, and then we'll get the other one. Okay, so if we have this and we have this MD, so this preview, so let's run this eval command and check. So check is basically just checking the IML file that's provided to make sure there are no errors. So let's go back to this guy and see what happens. So you kind of get this syntax error. You have the kind of highlighted thing. You have basically stuff that is kind of expected. And the reason why you can see here we're getting this because else is expecting something else. So you can see the same kind of error. So it's not finding what this else should be. So we can do this. Let's try to get another error. So this is type mismatch. And the reason why this is an error is because this is so IML is based on OCaml. We have integer and a string, and this is a big kind of no-no. So we need to add code to actually be able to define what it means to add integer to a string. So if we now run this, we should get, you have type error, etc. All of these things. Now, let me see this verification. So the files that we dumped and we fed to Claude just before we start to go into these individual files actually have a lot of information about what to do for these errors and many other errors. So effectively, there's lots of instructions for Claude to figure out what to do when it sees something like this, and kind of for all the different types of errors, especially when you're doing kind of heavy formal verification that requires tactics and goals, etc. So this is kind of simple, and any LLM will probably pick this up. But for kind of more advanced types of errors and where you need more help, there are things where basically in these files that are produced there's information there. So Claude will be able to kind of help you correct for this stuff. Okay, so let's go back and change this. So this is the first thing that we've done. Okay, so eval, by the way, let me actually, it's CodeLogician eval, so people know what the things we're going to be doing. So this is what we've done, kind of check to make sure that we're evaluating IML. There are no issues there. Then verification goals and check, listing them, checking them, decomps, and generating test cases. So those are kind of the big ones that we're going to be going through. Okay, so we've done this guy. So let's now start to admit some valid code, and it should be this guy right here. So just some code written IML. You can see here it is all correct, type checked, etc. So we should not have any problems going through this. So eval success. So this is a valid IML code that was given. Okay, great. Let us now go through the next one. So let's say list verification goals. So once we start going through things that have verification goals, so these are basically statements within verify. So you can see these are, again, Boolean valued functions that we want to mathematically verify that they're always true. So instance is, you can think of it as something that just looks for a counterexample. So in this case, you can see it's successful because it is actually identified. So, for x equals minus 11, this is false. So imagine you have a file with a bunch of these verify statements, and you want to extract not just their status, but let's say there are counterexamples, all sorts of things. And you want to have the machinery that, for Claude, for example, when it generates a big file or whatever it's doing, you can enumerate and you can get each one out successfully. So that kind of this agentic loop works well because, if it's just kind of all over the place, you'll still be able to identify it one by one and kind of enumerate and go through it. Okay, let us again go to preview. So we have this file, and let's try running this guy. Okay, so we now have lists. So we have listed these things. So let us now go through and individually formally verify them. Yeah, so you see lots of basically outputs. So this is all proved, and you'll see this pre-printed basically deduction of what the premises are, etc. So all of these things. So let's also now look for this instance. Sorry, this annoying preview thing. So this is now, if you remember, here we're just looking for the instance. So let's see how we can get out of that. Okay, so now what's actually special here, you can see, is when we get a counterexample, what it is important is it is actually a kind of a full model. So you can see that this is an actual valid IML value. And what is important, obviously, this is a very simple example, but for once you're doing heavy duty reasoning, not only can these counterexamples become very complex, sometimes we're talking about, pages of basically IML code for really advanced systems, like, for example, a sequence of fix, which is this protocol that's used in trading, fix messages into an exchange, and you can ask it, like, under what conditions, or like, this will always work, and you get a counterexample that spans basically pages code. And what's one of the main advances that are within Imandra is you can then basically this counterexample, you can compute with it immediately. So you can actually plug it into this code, and you can get Claude to do it, and you will actually say, okay, well, for this case, this is where this verification goal breaks down. So we can see here the source code produced. So this is valid IML code. And Claude also now knows how to do this. Okay, so we've done that. Let us also go through basically all of these things all at once. So yeah, you can see here, and you can see they're kind of out of order because it's all done in parallel. Um, but yeah, you can see very clearly we have basically for all of those either verify or instance statements, we got the output back. And you can do this again by just doing this check all command. Okay. So let us now proceed to decomposition requests. So again, eval, let's decomps. So why don't we go into this guy? So we have, so again, imandrax.dev page, that is really going to give you a lot of insight in what decomposition is. But what it does is it basically decomposes the state space into a finite number of symbolic regions. And this is really important when you're using basically this logical approaches for reasoning about really complex systems. This was developed at Imandra, and this is very much kind of, let's say, motivated by something called cylindrical algebraic decomposition. And the nature of that is outside the scope of this call, but it's easy to look up, and there's lots of documentation on our website for this. But the big idea is, traditionally, when you're thinking about testing, if you go to, a large enterprise and you go into the QA department, and if you ask somebody, are you rigorously testing these systems that you have or software? They will always tell you, yes, of course we do. And then you will ask them, you can ask them to, specify exactly what does that mean? What does it mean to rigorously test a system? And that's when they'll either say, well, we kind of spend a lot of time doing it, or we have 1,000 test cases, or we spent, a lot of money on this stuff. What we have developed is a kind of scientific mathematical way to define what does it mean. Let's say you have a model of a system and you want to really think about all of the edge cases. How do you go about this? And so this decomposition of a system is kind of the main workhorse that we use for that. We're able to take typically models that have infinitely many, or virtually infinitely many possible inputs and outputs, and we want to decompose the state space into a finite number of symbolic regions that share constraints in the invariant result. And so this is what you're looking at here. You can, in the Imandra, you can just basically run this decomp command and top this, and there's lots of other bells and whistles that we can add. I'll show you one in a second, but this will produce this output. So if we go back to our command here, so let us you can say it basically here is it is now decomposing these things, and it is basically identified different regions of that very simple function. And for each one, you can say basically what the constraints are, um, and what the invariant result is. So if I go back to this guy, clamp right here. Yeah. So um, what it has done is it basically said, okay, here are 3 edge cases where this happens. Now, again, this is a very simple example, but if you go to imandrax.dev or any other website, we have lots of articles in this. This really shines when you have, let's say, I'll just use one example, model of an exchange where you have lots of orders. You have an order book with orders, and you have lots of logic that defines what happens next. And so there you have, really infinitely many possible order books, concrete instances of order books going in, but um, there is a finite number of symbolic edge cases. And so this machinery is designed for that. So, okay, but with this, you can see you can actually get this the output back. So let us go through. Okay. Similarly to what we just did with verification goals, we should also just be able to get all of the, yeah, so all of these things at once. And you can see here kind of what the regions are. So you can see basically that function was just decomposed into these non-overlapping regions. Okay, so I mentioned before that this is kind of the foundation, and we can add a lot of other functionality that you really need once you're dealing with real world kind of systems. And one such feature is what's called a side condition. So you can add it via assuming command. And if we go to this guy, so you can see that this discount function takes a customer, which has this type, and it has basically returns a real value. So we can decompose this, and so it'll give us basically all of the edge cases, how this can work out. But let's say we want to focus on just the certain part of the state space of this. So, for example, in a kind of real world setting, this could be something where, let's say, you have an exchange, or you have some controller for a vehicle, or let's say it's even like a Stripe um, state machine model of how you use Stripe to accept payments, um, and you just want to say, okay, well, okay, there is, let's say, 100 different regions, but really, I only care about conditions when the following is true, and I want to focus on that. You can add that with the side condition, and side condition is just a function that takes this is C. You can see customer because when I have to basically define it, because it does type checking, so type inference, and it figures out that this must be of type customer. So basically, this valid C is a function that takes customer type, we'll call it C here, and returns a true or false. And what we do when we're running this decomposition, where now you can see where we have added this function as a side condition. So what we will get as the output is all of the regions of this function that satisfy effectively this constraint. So, and you can see what the kind of the logic is. So it's not going to, for example, here there is an age greater than 65, etc. This will, you know, make sure that this is always, even if, let's say, we change this to, let's say, 100. And this function discount. So there's a decomp command associated with this function definition. Okay, and let's now go and try to get out what its value is. Okay, so let's figure out what has happened. So we have this function that does some comparison. So customer has age, is member, and kind of total. So here we check if, okay, if it's a member, then we do these things. The customer is a member, then etc. So you can see age, there's condition 65 in both cases. But what we have since done, so this is kind of slightly outdated, for go list this guy, we have now added this constraint that the age must be over 100 or equals to 100. And so you can see this logic here, 65, everything shows up, but now actually this is 100. And so when we look at this guy, you can see constraints. We have two regions, and in both cases, age is greater than or equal to 100. So when these two things are true, then you have basically you can lend those things. So if we, for example, just assume, let's just see what happens here. Yeah, so let me just So what we've just now done is we remove the site condition, and you can see lots of these kind of basically regions. So these are all the edge cases of how this function performs. And model eval string. This is basically this is the invariant result. So this is the symbolic definition. What is the outcome of running this function when you have these constraints satisfied? This model eval string and model string, these are concrete sample points that you can use as an example. So basically what it's saying is, again, so when we ran this decomposition on this function discount, it produced us 1, 2, 3, 4 distinct regions of how this behaves. And kind of, you can see from the structure over here, this kind of makes sense because there's uh, 1, 2, 3. Yeah, there's 3 if statements and then else. So you get these 4 regions. And each region is defined by these constraints on the inputs, and kind of the invariant result is the expected output. And so these things are symbolic. These things are concrete instances that satisfy those constraints. And then basically what happens is inside Imandra X will run the model on these inputs that satisfy the constraints, and this will be the concrete output of that. So this matches here because it knows symbolically the only way that this can be is 0. Okay, so you can see here there are 4 regions. So let's go back to this guy. And let's rerun this. So we have 4. Now that we have added constraints, you would expect there to be less. And that's exactly what you're seeing. So now all of these things are basically age is greater than or equal to 100. So from 4, we just went down to 2 because we added this condition that these things must be true for all inputs into this time. Okay. All right. So hopefully that is clear. So, okay. So let's now extend this. So we've just shown you that we can generate effectively, we can take a function and really understand what are the different edge cases. We can superimpose a site condition via the assumption parameter, assuming parameter, which just takes a reference to a Boolean valued function that has the same kind of signature inputs as the function we're decomposing. And then we want to say, okay, well, now let's try to generate test cases. So instead of those kind of model eval string that we've shown, let's actually now generate test cases in the 2 languages that we support, Python and TypeScript. And between the 2 of those, any LLM will be able to just translate it to pretty much anything else that you want. Okay, so let us now, you can see this other command we're now using, gentest, and it's not available on all platforms. I think on Windows via the kind of the built-in Linux command this works, but maybe not on Windows directly. But check out the website. So if you're Mac or Linux, you're safe. Um, Windows is questionable, at least not the Linux within Windows. Okay, so let us now run this command and hope, yeah. So now we're actually seeing these. So this is valid Python code. So you can see here, again, we're taking that function, the discount, and generated Python code that now is, it has all of these constraints here. It has the invariant result. So again, this is what is the expected output of running this function on when the inputs satisfy these constraints. And you can see invariant, will typically be, unless it's, a very simple case, like here, it just says, okay, this will always be basically 0, real value 0. Here, you'll see that this is actually symbolic in the sense we're not like if whatever the c.total input, it could be 0, could be 100, could be minus 1,000, etc. The output of running that function when these things are true will always be that. So you can see this. So we just generated Python code out of this guy. Okay, if we go to, okay, let me just show you. So similarly, we can get, let's say, TypeScript. Oh yeah, saving. This is saving to a file. So if we go to here, yeah, you now have this basically as TypeScript code. Okay, so yeah, I won't run this, but it's basically it's just a different decomp file, but you'll get this kind of working stuff. So okay, so we've kind of gone through the functions. What I wanted to go to next is this article that we published. Yes, so this is this article that we published, I think, a few weeks ago or a week ago, where we analyze um, Stripe integration. So basically, the problem statement is um, Python code that is the backend implementation of something that connects to Stripe and accepts payments. Fairly complicated. If you just go to stripe.com, look at their API, they can get very complicated, especially because you have these various different kind of ways to accept payments, etc. So this is where you definitely want to use formal logic when you're, especially if you're byte coding stuff, etc. This is prime example of where this adds a lot of value. Let me just go. Okay. So this is the code that we want to formalize. So you can see there's a lot of kind of Python. It's pretty heavy, and it's using Stripe API to perform these kind of payments, etc. So it's fairly complicated, and the Stripe API itself is fairly complicated. So again, this is not where you just want to let loose Claude Code or really any LLM. You want to bring in logical reasoning, and this example that we describe on this website will walk you kind of through this stuff. And the big kind of outcome for this is uh, you ask Claude Code to say, hey, go and formalize this Python file. And what it produces is basically something like this. So after it learns IML, after it learns how to do all of this region decomps, verification goals, etc., it basically produces this, and it starts to write out properties that it thinks should just be true of this setup. So logically, they have to work, and very quickly it realizes that um, basically there are counterexamples to the logic that I thought was actually it must be true. And so that way, Claude actually figures out that this is okay. So there is actually um, basically this, I think, yes. So Claude wrote this statement, and Imandra X by CodeLogician actually said, no, there's a counterexample. And you can see my property was wrong. So this is from perspective Claude. And then went back and actually fixed the IML model. And then from the fixed IML model, it made sure that all of the verification goals, everything else is kind of correct, and then made the change to the original Python code. And the next kind of, let's say, thing that we wanted to do with the Stripe payments, you can see the kind of the code is also in the repository, is we wanted to add two new features. So this kind of high risk, so adding more complex state machine kind of transitions. So that's the first. And the second is this kind of 3DS. So this is this kind of new security feature that Stripe has. So you can see here, there's like these predicates that were basically the logic became much more complex, and the 5 verification goals were written, and then something broke. Basically, I had to go and fix them, and then it then made sure that the new model is correct. All of the verification goals pass. It understood all of the different edge cases that it has, in this case 53. And you can see here, like Claude to enumerate, I would have produced maybe a 10, but 53. So basically Claude said, listen, there are about 8 to 10 edge cases. After using CodeLogician, you got 53 out. And then we used this command, we just went through gen test to generate Python test cases. And so again, we started with Python. We got Claude to use CodeLogician to formalize the logic in IML. We made sure that the logic is correct. And then we added features to it. We made sure that the new features are behaving in the correct way. And then we use the new model IML to generate Python code, Python test cases, which we're then applying to the updated Python file. Yeah. So this is a great example of where you want to plug in logic and how using Claude Code can really be really incredible interface to things that historically were just difficult to use. So people had to learn Camel, etc. Now, really anyone can access this technology. So let's go back to these guys. So actually, let me just come up with something. Hey, generate some model in IML and try to verify something useful about it. So we'll just check that Claude can actually do this. But while it's working on that stuff, oh yeah, so I'll model a simple bank account, deposit withdrawal operations, verify that the balance stays non-zero. Okay, let's go. Let's go with this. You can see that's not something prepared, we're just kind of going for it. Actually, let me see this. So light command is just the eval. While we're working on this, if anyone has any questions, please ask. We'd love to answer them. Up in chats. I'm just kind of following up on this. I have no idea what model it's going to do, but let's see what. So it's actually producing right now code that it cannot. It's now going for an automated way to verify something that has recursion. Actually, let me go through. It's now going to kind of specific. So when you want to verify things up to, let's say, over, like let's say lists or something like that, you have to really reason about many different. You have to create an induction kind of principle for this. So Imandra has this incredible way to automate a lot of these kind of inductive steps and hypotheses and extract all of these other things. So you can really kind of scale this to really any type of formal verification you want to do about any kind of types of systems. It also has things that are kind of tests. So where we actually just test for, let's say, up to certain unrolling, let's say you want to unroll a function, a recursive function up to, let's say, degree 50 or 100 or something. It also has that. So it has this nice balance of built-in model checking and also this ability to kind of what's referred to here as waterfall, where you're creating the full kind of statement about infinitely many possible results via the induction statements. So what it basically said is, um, basically it verified something where the unroll statement could not find something, and it is now trying to go and make it more precise. So actually, don't worry about recursion because it's something. It's definitely outside the scope of this introductory um, 1 hour. But if you go to amandrax.dev, you will see lots of documentation specifically on that. And most of the time, if you're dealing with real world systems, kind of this unrolling up to a certain degree will be sufficient. But if you want to take it all the way to formally verify for infinitely many possible inputs and sequences of, let's say, events, you can also do this. But it will require this kind of rewrite rules and automated kind of induction, etc. And so Claude just went all the way in to the unroll the logic to be non-recursive. We also have a feature that's coming soon, which is kind of relevant to this, um, where we are kind of using what we call testing, where we um, just randomly sampling, let's say, verification goals and things like this, where it, it makes it very easy when there are certain counterexamples, certain structure of counterexamples that is easy to identify even without doing some heavy lifting in logic statements. We can kind of get the results back. So that's another thing that's coming soon, which will make it even kind of easier to identify. Um, so this right here is the code that I wrote. You can see here, all of these are basically different verification statements and transactions, etc. Um, but actually, for next week, this is actually a great segue. Let me come up with a nice introductory um, video of how to reason about kind of recursion and other things like that in a way where we can easily for kind of scope out things that we want to verify and how to scale it for those kind of, let's say, functions. They take arbitrary lists and things like this. So, but yeah, you can see here. So wrote some code, verified it, and using all of these kind of the functions that we um, taught it by installing CodeLogician and then learning how to use it from the kind of the dump that we produce out of the doc command. So we have 5 minutes left. So if there are any questions, would love to take them. But otherwise, yeah, just would love for you guys to install it, start using this thing. And if you have any questions, we have forum, which the link is on all of our websites. Please don't hesitate to ask questions. We also have contact email, which is, I think, just contact@imandra.ai. And would love to work with anyone and answer any questions. Awesome. Thank you very much. See you soon.